Yeah, that's a different kind, yeah. So separation, ionization, dissociation were the three terms we looked at. We kind of spent a little bit of time on dissociation. If you remember, I kind of showed you those ionic compounds, what happens when you put them into water, they dissociate, they break into individual ions. And we did a lot on dissociation that day. We talked about, if I took this beaker with ions and this beaker with ions, I mixed them together. We talked about the solubility chart, which is that selective precipitation idea kind of thing. So that was all lesson one stuff. Today we're going to kind of focus more on something called ionization, which is acids. And more specifically, we're going to talk about how do we name acids. And this is pretty important. This is going to be important for not only this unit, because if we don't know what kind of acid we're talking about, that's going to be a problem. Not only for this unit, but also for the entire year as well, and as well for Chem 30 as well. So you'll need to know how to name acids. So here we go here. Please follow along. Make sure you guys are paying attention here. You've pretty much had your cell phone time here today, so hopefully this will take about 20 minutes or so, and you'll have a little bit of time to work here on some homework here. So today we're going to talk about naming acids. It says here the following. Oops, just give me a second here. There we go. Acids are compounds that contain hydrogen, and it will ionize when dissolved into water. So again, we talk about that process of ionization. Okay. When acids are dissolved to form an aqueous solution, the hydrogen ion and an anion are produced. Okay. Two very important parts here. So for example, remember we have some HCl, for example, that's a gas. We need to put HCl gas into water so it can ionize into these two. Okay. All acids will produce this ion here, which is the hydrogen ion. That's why, for example, if you put pH paper into an acid, or if you put litmus paper into an acid, or if you put a pH meter into a solution, it measures this ion right here specifically. How many of these do we have? And what concentration is that, basically? How concentrated is it? Okay. All acids make H+. That's kind of the thing with acids. So because all acids make H+, we're going to focus a little bit on this ion a little bit specifically, because that's the ion that's going to kind of tell us the different acid types. Okay. So since all acids contain the hydrogen ion, the name of the acid is determined by the anion present quite often. Okay. There's two different ways to name acids. One is called IUPAC, which stands for International Union of Pure and Applied Chemistry, which is basically kind of a convention thing. So it says here we're going to name the acid as an ionic compound, because really that's what happens when we put it into water. We get an ionic compound, we get ions. And we're going to name it like that, and we're going to put the word aqueous in front. So if we're looking at these three examples, I'd call this one here, you guys can write this in, aqueous. Okay, and then we're going to have the hydrogen ion, of course, so hydrogen. And then we're going to name the last part here, which of course is a polyatomic ion, which we're going to call carbonate in this case, CO3 with a 2- charge, aqueous hydrogen carbonate. Okay, make sure you write that down. Again, this comes from the fact that H is a 1+, carbonate, if we look that up, is a 2-. Okay, and that's really where that comes from. Again, you're probably going to need your periodic tables out, which you guys should have your own copies of course, and you're going to need some to look at those polyatomic ions and make sure that you understand where these names are coming from. Okay, this one here is H, which is a 1+, of course, and then Br-, swap, drop, and reduce, of course, is kind of where we came up with that formula. So this would be called aqueous, and sometimes we could just abbreviate it as fine as well, hydrogen. And Br1-, of course, is bromide. Okay, don't forget bromide, chloride, iodide, etc., etc. Okay, good. This one here, okay, would be an H1+, of course. H is always a 1+ because it's going to form that ion, that's hydrogen ion. And then PO2 actually comes in a 3- charge. Now, if you went to go find that on the periodic table, you wouldn't find that there because PO2 is not there. But remember, this goes way back to like Unit 1, Lesson 3 or 4, I think, where we talk about PO2 is not there, but PO4 is. And PO4 with a 3- charge would be phosphate. PO3 would be phosphite. and PO2 would be actually hypophosphite. So that's what we need to put with this one here. So if you get a little bit confused with those, you're going to have to kind of go back and find that little list that we have on how to do those. Hypophosphite. Hypophosphite. Okay? And that's what we would call that one there. Aqueous hydrogen hypophosphite. Good? Questions, anyone? Again, we just put aqueous in front. All acids have hydrogen. We can see that here by looking at these three names. And then, of course, we just name the negative anion. Okay. Now, what we're going to do for the next part, so that's one of the ways to name acids. It's called IUPAC. The second way is something called the classical name. And the classical name, okay, actually, I'm just going to keep it right about here right now. The classical name, okay, it says the type of anion determines what the name is going to be. So again, we know that all acids are aqueous hydrogen. So that doesn't really matter to me a whole lot. And what I'm going to focus on now is the negative ion, the negative anion, or the negative ion, I should say. So if it ends in "ide", I'm going to change it to this hydroblank acid. If it ends in an "ate", I'm going to change it to ic acid. And if it ends in "ite", I'm going to change it to OS. Okay, and I'll give you some examples of that because I know that's like, well, I don't know what you're talking about right now. But we have some examples here now. Now, you don't have to make this exact same chart. In fact, if I were you, what I would do here, and again, I would not worry about this right here. I mean, you can, it's fine. If you can still see it, that's fine. But let's just kind of make a little chart here for ourselves and make it somewhat quickly if you can. And then we'll kind of pick this up here and we'll go through each one of these. And I'll kind of show you how these names are based on that naming system or that rule system. Okay. So again, it ends in "ide", so we got this hydro-ic thing, and then the blank part is going to be the chlor from that negative ion. Okay. Now let's go to the next one here. If that's okay, I'm going to go to here. This one here. So I got HClO4. That is known as. Let me just erase a little bit here because. Oops. Okay. So that's known as aqueous hydrogen. And ClO4 is a 1-. That is in the top left of the periodic table. That is called perchlorate. Okay, that one's actually one of the ones listed for you. So that is perchlorate. Again, I look at this negative part right here, and I see it says 8, and 8 and ic go together. So that's going back up to this one now. There's 8, and there's ic. So I'm on the second one, the second rule. 8 turns into ic, so I'm going to call this one perchlor. Okay, that would be this root here, basically. That's this part here, perchlor, and then the 8 changes to an ic, so it becomes perchloric acid. Okay, is that okay? So ic and 8 go together, and again, the roots kind of stay the roots of those negative ions. We're just changing 8 to ic, or we're changing the "ide" in the first one to hydroblankic acid. This one here would be aqueous hydrogen. I'm going to abbreviate that one. Chlorate. Okay, polyatomic ion. Again, because that's the root of the word right there, chlor. And then I got this 8 part right here. That 8 is going to change to ic. So again, I'm going to drop the 8. I'm going to put the ic on. I'm going to still use the root of the word chloric acid. Okay, a little different than the other one. Of course, the other one was perchloric acid. This is chloric acid. Okay, this one down here is aqueous hydrogen chlorite. And when I see "ite" here, okay, then I know that going back up to my notes here, basically that's this bottom one now. "Ite" has to change into OS. Okay, so I changed the "ite" into OS. And if you want to do that right first, there you go. There's "ite" and OS. Those two parts go together. Now I just put the root of the word. So in this case, chlorite becomes, oops, kind of missed there, chlorous acid. Okay, and that should be all one word there, of course. Chlorous acid. My pen's not great, so I apologize. Chlorous acid. Okay. And there's actually one more that's not on this thing here, so we'll just write that down here. HClO, or you might actually see HOCl. Okay, one of those two. They're really the same thing. You'll probably actually see this one because that's actually, if you connected it together, you'd probably see that. That's how it'd be formed together probably. So if we had that one, again, that's aqueous hydrogen. This is called hypochlorite. Again, this is on the periodic table. Ends in ite, so we got to change it to OS. Okay, so this becomes hypochlorous acid. Okay, the only thing that changes really is the ite goes to OS, the eights go to ic. The ides are a little trickier because we got to put the hydro in front and then the ic. Okay, is that okay? Any questions so far? Anyone? Questions? Questions? Now, I'm going to give you just a couple practice ones real quick, but then we have to talk about some special circumstances, unfortunately, and there's two of them that we'll talk about. But is that okay? Any questions so far? Okay. All right. There we go. So I'm just going to give you three to do real quick here, just for a little practice, just to make sure we're on the right page here. I'm going to give you that one. Let's give you can I what? Move up like this. Is that good? H. I got to be careful here. Let's go with H3N, I guess. And that's not what I did last class, though. I don't remember what I did last class. And HNO2. We'll go with those three, I guess. Good enough. Okay. Just do those three real quick. And so when we deal with, here, let's wait. I'm trying to record here, but sorry. So just, I'm just going to show that up on the screen. But if you missed the first part there, it's aqueous hydrogen nitrate, nitric, aqueous hydrogen nitride, which is hydronitric acid, and then the aqueous hydrogen nitrite becomes nitrous acid. Now, the two special circumstances are sulfur and phosphorus. If you're dealing with one of these, the root is not quite the root of the word. So we just don't drop certain parts. We have to drop a little bit and then put a little bit back on. So pretty good examples of this would be stuff that looks like this, H2SO4. Okay, so go ahead and write this one down. This would, of course, be aqueous. This is not any different, aqueous hydrogen sulfate. Okay, H is a 1 plus, SO4 is a 2 minus, of course. Swap and drop, that's where we get these formulas from. We're going to do ionic compounds, swap and drop. Now, aqueous hydrogen sulfate, it ends in 8, so I know that I need to have basically ic acid. Okay, so of course we talked about earlier, here's the root of this. This is sulf. Okay, so I'm going to put the sulf right here, but because it is sulfur based, the other one is phosphorus, but in sulfur based ones, we need to put, not just chop it off there, but we need to put that UR back on. So this is actually going to be sulfuric acid. Okay, so there's a little bit extra that we need to do with sulfur-based ones. I'll give you one more, for example. Let's go with H2SO3, okay, which would be aqueous, as we know, hydrogen sulfite. Yeah. Microx after school. I won't be there. Not that funny, actually. Kind of sad. So it ends in ite. So again, we know that that's going to be OS acid. Now, again, the root is sulf, but because it's a sulfur one, we need to put the UR back on. Okay, so it becomes sulfurous acid. Okay. Same would be the same thing would happen if it was aqueous hydrogen sulfide. So sulfide, we put the hydrosulfuric acid on. Okay. The other option is the phosphorus ones that we need to be a little careful of. Hopefully you guys are okay with that if I move it up there. So let's say we got some H3PO4. Okay. That's aqueous hydrogen phosphate. And again, real quick here, we're almost done. 8 is going to change into ic, so I know that. Perfect. Okay, 8 and ic go together. But this is a phosphorus one now, so there's my root here. Phospha and phospha. And I got to put the OR back on this time because phosphorus is spelled with an OR. So I got to put the OR back on. So this would be phosphoric acid in this case. Okay. Phosphoric acid. Okay. This only happens with sulfur ones, UR, and phosphorus OR. Okay. And real quick, just for maybe the hardest one here, H3P. This would be aqueous hydrogen. I'm going to do this a little quicker here. Phosphide. Okay. Aqueous hydrogen phosphide. And again, enzinide. So this is where I got to go, okay, well, that's a hydroic acid, enzinide. So what am I going to put in the middle? Again, that comes down to this part right here. That'd be phospha. And then I got to put the OR back on. Okay. Hydrophosphoric acid. Okay, good. Questions, anyone? Okay. If there is, just yell them out. That's fine. Mrs. Fletcher is going to give you guys a worksheet, and gals, and I'll try and bring it up here, but it's pretty self-explanatory. Just make sure, you're going to be filling in different parts, formulas, / classical name, IUPAC name kind of stuff. Let's have this done for tomorrow, please. Okay, this is your practice for today. I don't actually have a copy of that. That's fine. But we should be okay for that for tomorrow. Okay, please have that done.